Hi, I am Varun Joshi and welcome to day 11 of our Certified Kubernetes Administrator 2025 course. Not everyone comes from a software development background, so before diving into Kubernetes services, I want to briefly introduce some common software design patterns that you will frequently encounter in Kubernetes. We'll explore why the three-tier architecture emerged, what it is, and how microservices evolved from it. Additionally, we'll take a quick look at earlier design pattern that existed before the three-tier model to provide some historical context. Why and what of a three-tier architecture? Previously, when development started, everything was deployed as a single code base. If you had, let's say, an application that just served hello world, along with it allowed you to upload certain files, it also had an FTP server, then everything was deployed as a single chunk of code. When application is deployed as a single code base, it becomes tightly coupled. All your components, the UI, the backend, the data tier, all of these things are a single code base. Fixing one thing could break other parts. Hence, a tightly coupled system pose certain challenges. Second is difficult maintenance and upgrades. Now, since everything is together, if you were fixing one part, it could break the other part. This makes testing also difficult. Third is limited scalability. If our application's FTP server require more resources because let's say users were uploading files at a greater pace, then we would only want to scale the FTP server, but that option was not available. Hence limited scalability. Lastly, lack of flexibility in development. Development was slower due to dependency across components, making changes prone to errors. This design evolved and this evolved into a three-tier architecture. Three-tier architecture says break the code base into three main tiers. First tier will be the web tier, that is also called the front end. Second tier will be an application tier, which is also called a backend, and the third one will be the data tier, which will act as a database. What is web tier and front end? This, if you log in into amazon.com, what you see on screen when you go to the home page or you click on a product, that is part of the front end. That is what the user sees. Then there is an application tier. Application tier is something that works behind the scene. This user won't see the application tier. This user will only see the web tier, that is the front end. The application tier is the one that holds the business logic and communicates with the data tier. If I give you an example, let's say we are working on amazon.com. This user has a wish list. The logic for what happens when user clicks on wish list is in application tier, and it is then the application tier communicates with the data tier to see what all products are there in this user's wish list. And once the application tier has it, the web tier displays those results to the user. So this is a very high level at which the three-tier design works. The third one is the data tier, which holds your databases. I've also shown a middleware component, which is an important part of any software design in modern application development. Middleware facilitates the communication between the web tier and the application tier. But why do we need middleware to begin with? When we talk about modern applications, if I'm talking, let's say, about an e-commerce website, the core purpose of that e-commerce website is to sell products and display the products in such a way that users are truly interested. Secondly, it should also make suggestions that this is a product that you might need because you purchased this product the last time. This time you might need this product. So these all are the qualities of a good e-commerce website. And this is called the core logic, the core function of the website. So anything that is not core falls in the middleware part. For example, authentication. It's It's part of the application as a whole, but it is not part of the business logic. As a user, I don't care how authentication happens. Logging, monitoring, caching, API communication, and service coordination. Anything that is outside of the core functionality of the application falls under middleware. Now, there are several types of languages that you could be using to write each of these tiers. What I have written here are the most popular choices. If you are talking about front end, you would use HTML, CSS, JavaScript, React, Angular, Vue.js. In application tier, you could be using Python, Node.js, Java, Go, .NET. And then data tier could be using structured or unstructured databases. And the example for these could be MySQL, PostgreSQL, MongoDB, Redis. The database tier's functionality is to store, manage, and retrieve data. There is a middleware component here which has API gateway, Kafka, RabbitMQ. API gateway, see, whenever we are talking about a system, if one system wants to talk to another system, they expose something called APIs. The API is an entry point to a system. So API gateway is something that facilitates that communication. For example, here application tier would be exposing an API. Whenever web tier wants to communicate with the application tier, the request will first go to the API gateway, and then API gateway will tell, okay, you want to talk to the application tier, you should go here. The application architecture we are seeing right now, which has just 3 tiers, API gateway might not make sense, but once we move to the next part of this slide, we'll understand how useful an API gateway could be. Second one is Kafka. This is used to store and analyze streaming data. RabbitMQ, this is a simple queuing service. These are just examples of tools that you could be using in each component. This list is indicative, not exhaustive. Even when the application was broken down into 3 different tiers, there were still challenges with this design pattern. So let's see what are those challenges. First is scalability issue. But Varun, we also discussed about limited scalability in a single code-based design. Now that we have segregated this into web tier, application tier, and data tier, why would scalability be still a challenge? If I want to scale application tier, I can simply scale the application tier, and same applies to the web and data tier. What's the problem here? But I want you to understand, when you are dealing with a complex system as an e-commerce website, for example, you are deploying an e-commerce website here. Now, e-commerce website consists of many components. You will have product listing, you will have orders, wish list, and so on. If you are seeing heavy traffic, then your orders and product part will require more resources. Now, how do I only allocate more resources to those parts of the application? That's not possible, because all these parts are part of the application tier, because application tier is the one that holds the business logic. If my wish list component of the application tier is overly loaded, how do I ensure that only the wish list component has more resources? That is something that was not possible in this design. Hence, scalability issues were still there in a 3-tier architecture. Second is single point of failure. If, let's say, my application tier was down, then my application was essentially down. If my web tier was down, again my application was down. So hence, there were plenty of single point of failures in this design. Thirdly, slow development and deployment. This point is again copied from the initial challenge, because it was a single code base. It was a big code base. Changes were problems because changes could break the application. Here as well, application tier is one big piece. Anyone who is working on the wish list part of the entire stack might disturb the product listing part, because there is no logical separation. Everything is still together when I talk about the application tier. Same about the web tier. Web tier could be used by laptop users and mobile users. There was no segregation. This again caused slow development and deployment. Now, what is the solution that fixes all these problems for me? That is the microservices design. What are microservices? Before understanding what are microservices, let's see what we have done here. We still have the similar diagram, if not same. We still have a web tier, an application tier, we also have a data tier, and then there is a middleware. Then what is the difference? The difference is now we have broken down each chunk into smaller, independent, I'm stressing on the word independent services which communicate over APIs. I'll repeat the definition. Microservices are a design pattern where your application is broken down into smaller independent services which communicate over APIs. What is independent? Independent is, for example, if I want to scale product service, I can scale the product service because product service is independent of wishlist and of order service. If product service goes down, for example, then my users might not be able to see the latest inventory of products, but they will still be able to access the wishlist service. They might still be able to place order because the order service is still up. Similarly, if wishlist service is down, users will only not be able to access their wishlists, but everything else will continue to work as expected. Why we said that they communicate over API? Like I mentioned before, when your system is split into multiple subsystems, or even if you have a bigger system, then entry point to that system is an API. In this example, product service will expose an API, order service will expose an API, wishlist service will expose an API. As I mentioned before, middleware is the component that facilitates the communication between the web tier and the application tier. If a request comes to the web tier and user wants to access the wishlist, then API gateway service in the middleware will send that request to the wishlist service. If the user is trying to place an order, the API gateway will route that request to the order service. Hence, API gateway sends the request to the correct service. What are the benefits of a microservices design? First is scalability. If people are wishlisting products left, right, and center, I know they want resources in the wishlist service. I can only scale the wishlist service. Why I can do that? Because now I have independent services. Second is fault isolation. If something is wrong with my wishlist service, I know who will be the developers who will be working on this because wishlist service is already isolated. Third is faster deployments. I have smaller independent services. Hence, I can deploy my software, deploy my application in a faster manner. Fourth, technology flexibility. If you go back to this design, you would see that application tier could be using Python, Node.js, Java, Go, or .NET. This flexibility was already there, but with this microservices design, you get one notch above flexibility. What you can also do is you can have product service written in Java, and then you can have the wishlist service written in Python, order service written in Go. So you have that technology flexibility. Easier maintenance. Now, since we have broken down our application into smaller services, the maintenance is easier. So I hope now you understand how the architecture evolved. We started with a single code base, then we split the single code base into 3 tiers, then we further split the 3 tiers into different microservices. At present, you won't see this design because this is obsolete now, but this design is still prevalent. This design is the right way to deploy microservices. Now, there are other design patterns as well, like event-driven architecture. You would see queues, you will see serverless. But for now, whatever we have learned thus far will help us in our entire Kubernetes journey. Before I jump into this, up till now, we have only talked about software patterns. We have not talked about virtual machines, physical servers, or any container orchestration solution, or anything on which the application will run. We have not talked about that. So let's put the pieces onto a hardware so that we understand how the underlying hardware evolved based on these architectures. Initially, hold on, let me quickly bring a server here first. Oh, well, my camera is obstructing my view. Okay, I have a server here now. Now everything was deployed onto a single server. This server, if I talk about the pre-virtualization era, was a physical server. If I talk about the virtualization era, then you could also have a VM here. So that depends on which era you are talking and what sort of configuration was required to deploy this single code base. Maybe you required, let's say, 196 gigabytes of RAM. Spinning up a VM of that configuration at that point of time was not done. So you would have a physical server. If a smaller configuration was required, you could also have a VM. If a medium configuration was required, then you would also have a VM. So it depended on what sort of configuration that was needed and which era you were in. If virtualization didn't exist, then you had no option but to use a physical server. Then this design pattern evolved. I want you to understand that we have broken down the software into different chunks, but this software could still be deployed onto a single physical server or a single virtual machine. However, let's talk about the pre-virtualization era. This was one physical server where all the tiers were deployed. Bigger businesses who could afford more servers would be running more physical servers. Like one physical server was hosting the web tier, another physical server was hosting the application tier, then another physical server was hosting the data tier. You would have also seen a collapsed design wherein web tier and application tier were hosted on a single server and data tier was hosted on the one server. There are various permutations and combinations. When virtualization came in, all these three tiers were separated, but again you could also see a collapsed design. And like I mentioned before, this design is still prevalent. Now let's get to the topic of this course, Kubernetes. You can also have your web tier, your middleware, application tier and data tier run on containers, and those containers can be orchestrated using Kubernetes. Let's evolve this design further. Let me search for deployment. Okay, we have this deployment here. Web tier could be one deployment, application tier could be one deployment, and similarly data tier could be one deployment. Data tier could be one deployment. This is wrong. Data tier will have something called stateful sets. It is not deployment. I'm not able to find that object here. Hold on, let me stateful. I'm not able to find that object, but there is a Kubernetes object called stateful sets. We'll see what stateful sets are briefly in a little while, but we'll deep dive into them in greater detail in later part of this course. But for now, I want you to understand that this could be a deployment, this could be a deployment, and this will be a stateful set if this architecture is deployed onto Kubernetes. And in this course, we will be using the same architecture. We'll have a web tier, we'll have an application tier, and we'll have a data tier. All these things we'll be doing in this course. Having said that, in modern Kubernetes deployments, you will see that we have microservices. Since we are here for CKA certification, which is primarily done by infrastructure and OS admins. Hence, we are not using a microservices design. However, maybe in a later stage of this course, once this course is finished, we'll have a project wherein we'll be working with microservices. But for now, the architectural pattern, the software design pattern that we'll be using throughout this course is this one. We'll have a front end, back end, and a data tier. This is what we'll be doing. We won't have a middleware. Now let's see how microservices design worked. Again, physical servers were never used with microservices. I should not say never. There could be some corner use cases, but most of the deployments will not have physical servers at all these days, until and unless they require some high-end configuration. Can I use virtual machines with microservices? Of course. Web UI can be one virtual machine, mobile UI could be one virtual machine, and all these other services, each having their own virtual machine. That design is also present and works seamlessly, because microservices is not a hardware pattern, it's a software pattern. Now that software pattern can be deployed onto physical servers also, but you wouldn't do that because that's not optimal. You could deploy that microservices design of an application onto VMs, which you will see, but again, those use cases are limited. But microservices design of software is perfect for Kubernetes. For example, if this application were to be deployed onto Kubernetes, then web tier will have two deployments, one for web UI, one for mobile UI. Middleware part will have two deployments, one for API gateway and one for authentication service. And similarly, application tier will have three deployments. Hence, this application will constitute of 7 deployments. And here we have authentication service. This will be used to authenticate users who are logging in into our e-commerce website. Okay, I hope the design patterns and how they map onto hardware is also clear now. Let's now discuss this part. This is the meatier part. Why can't I use deployment in the database tier? Why do we need something called stateful sets? So let's understand that thing. Let me first move these a little up. When I talk about databases, databases are stateful in nature. What is stateful? Before we dive into that, let's come here. If my product service, why my product service is a deployment? If I have 3 pods in this deployment, for example, then each pod is a copy of another because each pod is a replica. That is what a deployment will do. It will create 3 replicas. If one of those pods goes down, then another pod will come up and users will be accessing my application the same way. If one pod is down, then a different pod can serve its purpose because product service as a whole is not storing any data. It is just business logic. It is communicating with the data tier or any data that the user has requested, but in itself the product service is not storing any data. Same applies to wishlist service. Wishlist service is just the logic, the business logic. Wishlist is not storing the items in the wishlist. The items that are part of the wishlist are stored in the database tier. When user is requesting for that data, wishlist service is communicating with the data tier and then displaying the user the wishlist via the web tier. Wishlist in itself is not storing any data. Hence, wishlist service or product service or order service are stateless in nature because they are not storing any data. Whereas the data tier, databases store data. Hence, they are stateful in nature. Why can't I use deployments for databases? Because not all instances or databases are same. One could be the master, another could be a mirror, and then the third one could also be a mirror. If you see this architecture here, let's say this is a stateful set for now. Master is replicating to mirror 1 and then mirror 1 is replicating to mirror 2. In deployments, that does not happen. All the replicas that exist in a deployment, all the pods that exist in the deployment, they are exactly the same purpose. If one goes down, another one could serve the purpose in the same way. When I talk about databases, 3 DB pods are not replicas. We know that. One could be the master, other 2 could be slaves, like we see in this design. Unique names. Each database server should have a unique name because the database administrator has configured the replication based on that. Hence, I require unique names for my databases. All these conditions are not met by deployments, but these are met by stateful sets, which is why databases use stateful sets. But Varun, why have you written typically hosted outside Kubernetes? Why haven't you mentioned stateful sets here? It is because when I talk about production grade applications, they deploy databases outside of Kubernetes because deploying databases onto Kubernetes is complex. handling replication, high availability, fault tolerance, all these could become a problem. That's why databases are deployed outside of Kubernetes. Am I saying that you will not see a design where databases are in the Kubernetes itself? Of course you will see those designs, because as the technology is evolving, we have something called Kubernetes operator. We will discuss this later, but briefly, Kubernetes operator is essentially a set of steps that replicates what a human would do. For example, operator can set up a MySQL or PostgreSQL, Prometheus, and there are operators for many things. These operators can be used to deploy the entire stack, and they will also handle replication for you, but they reduce the complexity. They do not remove the complexity entirely. Hence, it is suggested to have a data tier outside of Kubernetes in production design. We'll discuss on this when we discuss stateful sets, but for now I'll leave this here. I hope you now have an understanding of software patterns and how they fit into Kubernetes. That's a wrap for this lecture. In this lecture, we covered the fundamentals of 3-tier architecture and microservices, understanding their benefits and challenges. In the next lecture, we'll work with Kubernetes, which is essential for establishing communication between microservices and exposing applications to the outside world. We have not yet discussed how the API gateway will communicate with product service, how the API gateway will communicate with order service, how the mobile UI will communicate with API service, how it will communicate with authentication service. We have not discussed that. We'll discuss in details on those topics when we discuss Kubernetes services. This is a software pattern service. Okay, do not confuse this with Kubernetes service. Kubernetes service is something that we'll discuss in day 12. We'll have the same design, and then we'll have Kubernetes service, which will allow communication between these tiers. Anyway, if you have any questions, feel free to ask them in the comment section and I'll reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.